I'm going to talk about the technologies that we offer at AdaCore for cybersecurity. And that will be my last slide. So 3 important points to remember from this talk. With Ada and Spark and the tools that we provide at AdaCore, you already have a lot to defeat serious security vulnerabilities, more than in many other languages. Some of them were mentioned before. If you want to go further than that, we have static analysis tools, CodePeer for detecting vulnerabilities, Spark to completely prevent classes of vulnerabilities that you can use that we offer in our products. And if you want to go even further than that, please talk to us. So we are in the process of adding more features, more tools in the coming years, this year, next year, focused on cybersecurity, and I mentioned a few here. So first testing, compiler hardening, secure proven libraries, taint analysis. And here we will really focus the developments on the things that you ask us. So we have started discussing with some of you about what are your cybersecurity needs, and we'll need more of that in the future to better focus our efforts here. So I said that will be my last slide, so I'll keep that promise. But this is not now my last slide. I'm going to go into more details about that. So we started this year by realizing that security plays a much more important role in your industries. And we've come up with this web page that puts security on an equal footing with all the other domains where you operate. So avionics, ATM, space, rail, automotive, defense here. And this web page is the central point where we'll describe all our offers around cybersecurity. And we'll keep this page up to date if you want to know what new we have and if you are not coming to the tech days like this year. And one thing that we have on this page is this new book. So it's one of our bestsellers, if we can say such a thing for a book that we offer. And it lists all the things that we do around cybersecurity, what the languages provide, the Ada and Spark languages themselves, and what all the tools that we build around these languages provide on top of the base language capabilities. And I'll go into a bit more details in this presentation about the things that we discuss in this book, especially the top-level security vulnerabilities that you have to address when you do secure software. So one of the main security vulnerabilities has to do with validating inputs. And one serious security vulnerability around validating inputs is the SQL injection that was mentioned various times today. And here is a very concrete example of a SQL injection by our good friend XKCD, the comic strip. So you have a mother that is called by the school, and the school says that they lost all the student records. Why? Because they called their son Robert Tick, closing parentheses, semicolon, drop table students. What happens when you do that? That was mentioned by Bob this morning. If that string is just used inside a SQL query, this actual data will become code, will get executed, and you will drop all the students' data here. So that's a very dumb issue, and there are many more. So around validity of data, there are many simple things that can be defeated quite easily when you have a suitable language or tools. At the dynamic level, you can do a lot with just the Ada runtime checking. So Ada checks at very many places in your code that the data is proper for its type. So it's a strongly typed language. And you can have more of this checking by inserting your own checks for xtick valid. So that's Ada defined attributes that checks that x scalar or value x is valid in its type. Or the GNAT-specific attribute valid underscore scalars. So if you don't know about this one, you might find it useful in that context. This is applicable to any type in Ada, and it will check recursively down the fine-grained components of this record, or arrays of records, or array of records of arrays, that all of the individual scalars inside this big data piece are valid. So you can check that, and you can ask the compiler with this switch minus GNAT-v, so there's a sequence of switches that you can use here after this capital V, that inserts additional checks inside your code that are not mandated by the Ada standard, but that adds verifications when you execute your test in particular. So that's when you're executing tests, or if you want to keep runtime checking during the final execution. But you can also do things statically, so making sure that these kind of things cannot occur, and detecting things even without having the actual test case that will show the problem. And so you can do things with the GNAT warnings, or with code peer stat analysis, or with Spark Pro, so going in increasing power here of analysis. And with Spark Pro, we'll go into more details later, but proving that there are no runtime checks failures, or proving that there are specific contracts that you put in your code that are always respected by the code, related to validity. So static analysis is not the only way to augment the verification that you can do natively with testing. You can do fuzz testing. So fuzz testing exploits the native capability of the Ada language and of the compiler to insert these validity checks. Fuzz testing is a kind of random testing focused on a piece of software that is very good for low-level pieces of software like infrastructure code or codecs or network stacks. And you can find this blog post on AdaCore blogs. That's called Leveraging Ada Runtime Check with Fuzz Testing in AFL. That was written by one of our customers, so Lionel Mathias from Thales. So for this exercise, he used just open source technology, building his own integration of this AFL fuzzer with NAT. But this is something that we're working on right now to make it part of our product. And in this exercise, in the blog, he just discusses the many bugs he found in open libraries, but they also used it on their own product, live product at Thales, and they found dozens of bugs. So that's very interesting to find bugs, even if you don't have a test suite that exhibits the behavior. Now, if you don't capture all the things that a validity check should capture, you might run into other problems like the injection of code. So we're lucky in the Ada world is that most of the issues with Ada code injection, so if you're really injecting code at the source Ada level, are prevented because there's no reflection or eval construct in the language, because you can statically link your application, for example, if you don't want to suffer from the dynamic libraries being corrupted, because you can execute from ROM or Flash to ensure that the code itself is not corrupted. But you're always vulnerable, whatever language, to machine code injection. So that's the kind of things that typically would be possible if you do a buffer overflow that replaces the return address on the stack. And in languages like C, C++, you have many dynamic solutions that are not complete. So you have execute or write, you have stack canaries, you have many of these solutions that in Ada, you can have a much stronger solution that just builds on the Ada runtime checks. So buffer overflow in Ada, you can capture it immediately at runtime if you enable these kind of checks. And if you want to go beyond the dynamic checking, well, there's CodePeer and Spark Pro, which were mentioned before, which allow you to capture all of these possible failures statically and then decide which ones can be effectively exercised for security vulnerability. If you don't solve all of these issues, you might have a problem even with runtime checks where they fail at runtime. And that can lead to a DOS, a denial of service, where the application doesn't run anymore. So maybe the attacker cannot take control, but he can put the server down or the application down. Again, with Ada, we have both dynamic solutions and static solutions for that. So dynamically, you can catch exceptions. You can choose to restart the service. So that depends on the applicability in your context. And at the static level, there are two things that can lead to a DOS. There are crashes, and there are non-termination of the application, typically a loop that continues looping forever. And both of them can be targeted with CodePeer and Spark Pro. Now, turning to something a bit different. So far, we've discussed issues that are valid for both safety and security, namely integrity properties. When we look now at confidentiality, that's something that is new in the security world. That's the ability of not leaking information that you should keep secret to people in the outside world. And so if we look at all these CWEs except the one that I've hidden now, CodePeer and Spark already provide a good solution. because they are based on typically buffer overflows. Now, if we look at the last one, covert channel, we don't have a proper solution here today at AdaCore, but we are looking at possible solutions based on compiler hardening, so based on GNAT-Pro. So just a few more words about these covert channels. There are two sides of side channel attacks, so data leakage attacks and fault injection attacks. Data leakage can be very simply leaking data to someone who uses your API that you shouldn't have access to, or keeping data in the memory that is secret and that the attacker can look at, for example, through a different thread. Or something much more subtle, that's the execution time or the power consumption of your application depends on some secrets. And that can be whether, for example, a test in your code depends on secret data, but also that you're reading or writing an array that has secret data, and even that can be exploited by attackers. So it can be very subtle. Fault injection attacks are also quite scary. So it's the fact that with laser beams or power supply changes, the attacker can change the data on your computer. And so it can flip bits, it can corrupt data arbitrarily. It can also corrupt control, because the control is, for example, some data on your computer, like the program counter or the return address, can be corrupted. So the attacker can, for example, skip some important branch decisions to decide whether you're allowed to proceed to this secure area of the code. And against these kind of attacks, like I said, people have developed a number of techniques that they apply mostly manually, especially in the smart card business. And many of these techniques, we could have extension of the compiler of GCC to apply them more systematically when you need it. And so, for example, for data leakage attacks, well, there are techniques to erase the stack or the registers. And so, for example, this company, Mbecosm, has been doing that for LLVM and is planning to release that for GCC soon. And this is the kind of techniques that we could make available for Ada, C, C++ in the future. Similarly, for timing attacks, it's possible to analyze when the control depends on secret data, and then to make sure that, for example, comparison of arrays always take the same time, or reading or writing an array is done using a first random index so that you don't depend on the exact location of the secret data. So these kind of techniques can be automated, and that's where we're interested in knowing what would be useful for you. Same for the fault injection attacks. To defeat corruption of data, well, a well-known technique is to have a representation that is not unique, that is redundant, so that bit flip, for example, can be detected. So you have checksums or similar things in your data. And same for changing the control flow. So you can have counters, you can have ways to detect that not all of the instructions that should have been done in this loop, for example, that not all iterations were done. So there are ways to insert counters and check them to make sure that the control flow is not perverted. So all these can be automated. Again, we need to discuss with people who depend on these measures to be taken. Now, you'll see in the booklet that we've considered 4 broad areas where security needs to be tackled in different ways. And probably most of your projects fall into these 4 big areas. So the scenario 1 is identifying and repairing security in existing Ada code. And that's where you make the most of GNAT warnings. So first, you need to be aware that there are a lot of GNAT warnings. There are 50 kinds of GNAT warnings and more than 150 individual messages that can be issued. And CodePeer to go beyond what the simple analysis done in the GNAT compiler can do. But CodePeer has been discussed before and will be discussed later, so I won't go into much detail here. The scenario 2 is that you're developing Ada software and that you want to put best practices for security in place from the start. And here you can use, indeed, GNAT warnings and CodePeer, but also all the other tools that we provide for managing complexity of Ada code, like metric with GNAT metrics, metric computation, coding standards, verification with NAC check, all the tools we have at your disposal here. The third scenario is probably one which you're not the most familiar with, so I'll discuss it a bit later. Secure design using Spark. So that's where you can have the most secure guarantees about your program, even statically, without executing it. And the fourth scenario is when you mix these techniques, having a principled ways to cut the application in pieces so that guarantees, for example, on the most secure pieces do not depend on a possible fault in the less secure pieces. So I'll go now into two examples of this scenario 3 that are particularly telling, in my opinion. Muen. So these two examples are open source software. They're available on the web, so you can go check what they're doing. Muen is a separation kernel that is done jointly by the University of Rapperswil in Switzerland and secunet company in Germany. And since 2013, so that's what they said in 2013 already, the Muen separation kernel is the world's first open source microkernel that has been formally proved to contain no runtime errors at the source code level. And since their first release in 2013, they have kept evolving this kernel, maintaining this property. So that's really a rich property to get. They are working to get even more, so more functional properties of this kernel. But that's already a lot for this very critical piece of software that sits at the bottom of your application. Something as interesting, so that was mentioned by Jamie this morning, ANSSI, the French security agency. So in their own words, we're tired of auditing code from people selling pieces of software and systems to the French government that were supposed to be secure but were not. And so after the bad USB vulnerability in 2014, they decided to come up with a proper design of hardware, system, and software for having a safe USB key. So that's their Wookey project. And as part of this project, they created a small kernel that goes into the USB key. And this small kernel is written mostly in Spark and Ada. And they say that full classes of attacks, like buffer overflows, are mitigated in this kernel called EWOC, providing more confidence. How do they do that? By using Ada along with Spark. Again, everything is open source, so I recommend that you go see. And it's very encouraging to see people using Spark and Ada as an example of good software practices for security. So I didn't lie, that's my last slide. So Ada and Spark and the tools we provide already give you a lot for security. If you want to have more, we have static analysis tools, CodePR and Spark, and go talk to us if you have difficulties choosing between the two. And the last point, very important one, is that we want to move towards more features, more tools for cybersecurity in the future. So come talk to us if you have specific needs. Thank you. Next time.